In this section, we are going to talk about sensors in detail. First, let me introduce the definition of a sensor. Sensor detects changes in the ambient conditions or in the state of another device or a system and conveys or records this information in a certain manner. So that is the first definition about sensors. And then there are many definitions you can find on internet, and most of them are saying pretty much the same thing. So it is basically a device that detects a physical phenomena and then change the electrical signal, or it generates an electrical signal. In this figure, you can see another version of the different types of sensors we looked at earlier. So these are the common different sensors used in different IoT products and solutions, both in smart home domain and industrial domains. So have electric and magnetic, leak and level, force, load, tow, pressure, strain, flow sensors, chemical and gas, acoustics, sounds, vibrations, humidity, moisture, temperature, motion, velocity, displacement, position, presence, proximity, machine vision, optical, ambient light. So these are the most common ones, but there could be many sensors, as you can show in over the last few slides. In IoT system, sensors perform an input function by sensing or feeling physical changes and characteristics of a system in response to a stimuli. So basically, the sensors are the inputs for IoT system, which the system get to know what is happening around it. For example, heat is converted into an electrical signal by a temperature sensor, or the atmospheric pressure is converted to an electrical signal by a barometer. So all these sensors you can see. So some of the sensors you will be seeing in the labs. So these are sensor components that we use in prototyping with prototyping boards. So ultrasonic ranger, loudness, light and humidity, temperature and humidity, air quality, accelerometer and compass. You can find hundreds of different sensors like this, where you can connect to your prototyping boards and build IoT solutions. Each of them convert some kind of change in a real world into an electrical signal, and then we measure the electrical signal and determine what is the value of temperature, loudness, light, or whatever the parameter we are measuring. So transducers are important concept to understand when you're talking about sensors and actuators. Basically, the sensors and actuators both together we consider, or we call them, transducers. So transducer is a device that converts energy from one form to the other. So typically a transducer converts signal in one form of energy to a signal in another. You can see here we have put another definition as well, pretty much to say the same thing. And as you can see in the figure, transducer is an intermediary where they quantify physical quantity, converts into an analog signal. In this case, it is temperature. This figure clearly explains what the role of the transducer is. So as we show, first in a sound system, a microphone input device converts the sound waves into electrical signals for an amplifier to amplify. So this is the process. And when it comes to the loudspeaker, which is the output device, it converts the electrical signal into a sound wave. So this has both the sensor as well as the actuator combined in the single process. And it converts the energy twice. First, the sound wave into electrical signal, and then the electromagnetic wave into a sound wave. As I said before, transducers is the collective term used for both sensors as well as for actuators. So I have put up a video here about transducers, sensors and actuators. Please go and watch them to understand the role of transducers, sensors and actuators better. Transducers can be categorized into three categories based on which the direction of information passes through. We already talked about the sensors, where they convert a physical phenomena into a signal. The actuator does the opposite, which is that it converts a signal, electrical signal, into a physical phenomena. In the bidirectional transducers, does the both, where it converts the physical phenomena into electrical signal and then also convert electrical signal into physical phenomena. Sensors are typically sensitive to only one property that it's supposed to measure. For example, a temperature sensor is only sensitive to the ambient temperature of a room, so it measures the temperature. It responds the changes of the temperature. It is insensitive to any other property likely to be encountered in its application. For example, the temperature sensor does not bother about the light or the pressure while sensing the temperature. It does not influence the measurements. So the measuring temperature does not reduce or increase the temperature. So these are the primary features of a sensor. What is sensor resolution? The resolution of a sensor is the smallest change it can detect in the quantity that it is measuring. The resolution of a sensor with the digital output is usually the smallest resolution the digital output is capable of processing. So basically, if you are measuring temperature, it might have one digit like 27.1 or 27.15, and then the next increment, the smallest increment it might measure could be 27.6. So it could be like 0.1 or 0.01. So depending on the quality of the sensor, so the resolution is the smallest change that it can measure. The higher the resolution of a sensor, the more accurate it is the precision. However, the sensor's accuracy does not depend on the resolution. Let's say you have a temperature sensor which can only measure increment of 1 Celsius. So 25, 26, 27. But the actual temperature in a room could be 27.55. So when it is 27.55, the digital sensor might say 28 because it rounded up. So it is less accurate. But if you have a sensor resolution, another sensor which has a resolution of 0.1, it could go for 27.6 because 27.55 rounded up to 1 decimal place, which means 27.6. So 27.6 is more accurate than 28, which they rounded up 2 decimal places. However, if the second temperature that we were talking about, if it is some faulty sensor, it might show like 23.4. Just because it can measure additional 1 decimal, that doesn't mean it is accurate. So that is why here it says the more resolution of a sensor, the more accurate its precision. But the sensor's accuracy does not depend on its resolution. Sensors can be classified into different classes. First, based on output, and then based on data type. Based on output, we have 2 classes, analog sensors and digital sensors. Based on the data type, we have the scalar sensors and vector sensors. Over the next few slides, we will be discussing each of these classes in detail. First class of sensors we are going to look at are analog sensors, which are classified based on the output. Analog sensors produce a continuous output signal or a voltage, which is generally proportional to the quantity they are measuring. So basically, if you are measuring temperature, speed, pressure, the voltage is generated is proportionate to the value of the temperature. So physical quantities such as temperature, speed, displacement, all these quantities tend to be continuous in nature, because in temperature you see a continuous value in real world. And if you put a temperature or thermometer into a liquid or a hot drink, it will continuously rise up until to the temperature which matches of the liquid. So these kind of sensors, we call them analog sensors. Second category of sensors are digital sensors, again classified based on the output. So digital sensors produce a discrete digital output of signal or a voltage that are a digital representation of the quantity they measure. So digital sensors produce binary output signals such as 1 or 0 represent on or off. Digital signals only produce discrete or otherwise non-continuous values which may be output as a signal single bit. These digital sensors might also produce a byte if they are combined into parallel transmission. For example, if this particular digital sensor might want to measure a number of discrete levels, more than 2 like on and off, it might need to have parallel transmission lines which could be combined together to create a producer byte, which give enough categories or levels which can be used to denote different levels of outputs. The next class of sensors are scalar sensors, which classified based on the data type. So the scalar sensors produce output results, which is the signal or the voltage, which is generally proportional to the magnitude of the quantity being measured. For example, a physical quantity such as temperature, color, pressure, strain, all of these are scalar quantities where the magnitude is sufficient to convey the information. For example, temperature in a room can be measured using a thermometer or thermocoupler, which respond to temperature changes, irrespective of the orientation of the sensor or its direction. The final class we want to look at is the vector sensors, which classified based on the data type. So vector sensors produce output signal or the voltage, which is generally proportional to the magnitude as well as the direction and the orientation of the quality being measured. For example, physical quantities such as sound, image, velocity, acceleration, orientation are all vector quantities. So not only the magnitude matters, but also the direction and the orientation also need to be there in order to convey sufficient complete information. For example, the acceleration of a body can be measured by using acceleration, which gives the components of acceleration of the body with respect to x, y, z coordinate axis. Earlier in this lesson, I explained to you that when we talk about sensor types such as light, speed, sound, we are broadly talking about a category or a family of sensors. There are many different techniques people have developed to measure the same phenomena. For example, if you want to measure light, there are multiple ways to measure the light, fundamentally from technical point of view, which each of them has their own pros and cons. And then when you go to the implementation and the manufacturing, then there are many different variations within these conceptually different ways of developing sensors. For example, if you take temperature, which is the family of sensor type, and then there are two well-known approaches, which is the thermocouple and thermistor. And then when somebody is implementing these sensors and manufacturing, there could be many different thermocouplers and many different thermistors based on how they're going to implement, what kind of technology they use, and then the expected sensitivity and what kind of application they're going to use, and the cost of these sensors need to be at the end. So in this slide, I want to briefly show you different techniques where people have developed related to commonly used sensors to measure the same phenomena. So please pause the video and just do a Google search on each of these techniques and try to get familiar with the different techniques people have developed. Over the next few slides, I will introduce few of these techniques to demonstrate why people have come up with these different approaches. Let's look at two different ways to develop temperature sensors: thermocouple and thermistor. Thermocouple sensors contains two dissimilar metals. That is the main idea behind the thermocouple. Thermistor is where the resistance changes with the temperature. Please go and watch the video I have put here, where they have explained the two ideas in great detail. It will help you to understand the differences between the two techniques. Thermocouple-based temperature sensors are developed based on two different metal alloys. The Seebeck effect, which described as temperature difference between the two dissimilar electrical conductors or semiconductors, produce a voltage difference between the two substances. So you can clearly see the idea in the diagram, where you have metal A and B, and where you have the joint junction, where you increase the temperature. And then if you measure the difference between the two cold joints, you can get the voltage difference. So based on this voltage difference, you can calculate what is the temperature is. So large temperature range can be detected by using this technique from minus 250 Celsius to 300,000 Celsius. So the next type is thermistor resistance based temperature sensors. So thermistor resistance is depend on the temperature. So there are two different fundamental types of thermistors, where the negative temperature coefficient and the positive temperature coefficient. So the negative one, the resistance decreases as the temperature rises. In the positive one, the resistance increase as the temperature rises. Then you can basically monitor the changes of the resistance in the circuit and determine the temperature. There are a number of advantages and disadvantages in thermocouple sensors. So in thermocouple sensors, the advantages are they are simple, rugged, inexpensive, self-powered, and wide temperature range. The disadvantage is they are non-linear, low voltage, there's a reference requirement, least stable, and the least sensitive. So if you are looking for a simple, rugged, inexpensive solution with wide temperature range, a thermocouple is your best option. In thermistors, the advantages are high output, fast response time, and high sensitivity. The disadvantage is very fragile, non-linear, limited temperature range, and then the current source required, because you need to put the current and do the measurement. So if your application requires a high sensitive, fast response, high output, then the thermistor would be the best option. So likewise, each of the sensor that you pick for your IoT solution, you need to analyze the trade-offs, advantages and disadvantages, and then pick the best one that matches your particular application. Most of the time in IoT solution design, there will be no the best solution or the best sensor. It all depends on what you want to achieve, and pick the better one, not the perfect one, the better sensor to achieve the task you want to achieve. An important question that you need to think about when you are working with sensors is, why calibrate low-cost sensors? So variations due to manufacturing might yield slightly different readings from sensors even within the same production run. Differences in sensor design. Sensors respond differently under similar conditions, especially if they use different methods to measure the parameters. So we already talked about a couple of different temperature sensors which use different techniques to implement. They may be slightly behave in a slightly different ways in a very similar conditions. Sensors are also subject to shock, humidity, heat, cold during storage, transportation, assembly, may be the reason behind some of these changes. Some sensors age and their responses change over time. Sometimes you start sensing humidity or temperature, and then you will realize that it is offset by number of Celsius. So then you need to recalibrate either more software perspective or hardware perspective from software perspective, you can simply add, maybe if it is always 2 Celsius behind, you can add a couple of Celsius at the software layer once you get the data. But again, it depends on the how critical the application is. So if it is like smart home monitoring, of course you can do these adding kind of Celsius monitoring. But if you are doing some precise measurements, or otherwise like more damage would happen, like measuring the temperature of medicine storage, then actually you should not trust to just add a couple of temperature Celsius into the sensor readings at the software layer. Either you need to replace or do some hardware level calibration. In some cases, the digital to analog to digital converter is subject to the variability as well. I would like you to pause the video now and go and watch the video about the sensor calibration and why it is important. Previously, we discussed about temperature sensors. Especially we focus on 2 different methods that can be used to develop temperature sensors. Here we are going to focus on the relative humidity, and we are going to talk about 3 different ways to develop these humidity sensors. So relative humidity sensors measures the moisture and the temperature in the air and reports the relative humidity as a percentage of the ratio of the moisture in the air to the maximum amount that can be held in the air at that particular temperature. So the 3 techniques are capacitive, resistive, and thermal. A capacitive humidity sensor measures relative humidity by placing a thin stripe of metal oxide between 2 electrodes. The metal oxide's electrical capacity changes with the atmosphere's relative humidity. For example, the weather, commercial, and industrials are using these type of capacitive humidity sensors. The capacitive type sensors are linear and can measure relative humidity from 0 to 100%. The downside is the complex circuitry and regular calibration is required. In resistive humidity sensors, they utilizes ions in the salt to measure the electrical impedance of atoms. As humidity changes, so do the resistance of the electrodes on either sides of the salt medium. The third type is thermal. So in thermal relative humidity sensors, 2 thermal sensors conduct electricity based upon the humidity of the surrounding air. One sensor is encased in dry nitrogen while the other measures the ambient air. The difference between the 2 measures the humidity. This is a table of relative humidity sensors compared against different types. This table comes from a sensor manufacturer. I don't want to go into the details of this table, but the point I want to emphasize is that if you are looking for a very specific type of relative humidity sensor, you need to go into the details of the technical specification of each humidity sensor and pick the one that matches your requirement. Most of the time when we are talking about IoT systems, we broadly talk about humidity sensor, and some application, to be honest, like smart home, buildings, cities, picking a sensor is not going to be a quite challenging issue. You can review some of the existing and well used sensors and pick one. But if you're system is going to be very specific and niche one. For example, something that need to be precisely monitored, like medicine refrigerator or something like that, or transportation of medicine containers, which you need to be maintained in a very precise specified environment. Then you will need to invest quite a lot of time on selecting the most appropriate sensor. So far we talk about temperature and humidity. I'm not going to talk about any other sensors in this lesson in this detail, but the point I want to make is that for any sensor that you wish to use, there could be many different alternatives. So make sure, depending on the task you want to achieve, you do your own research into different methods and different implementations of these methods produced by different manufacturers and their price points, and come up with a trade-off to justify why did you pick a particular type of sensor for your application. There are a number of characteristics that you need to think about or consider when we are selecting sensors. There are range, accuracy, precision, resolution, sensitivity, hysteresis, linearity, and response time. Let us go through one by one. Range is the maximum and minimum value which the sensors work well and can measure. So the maximum and minimum value of temperature or humidity or whatever the sensor you're looking at. Accuracy is given an absolute standard. Accuracy is the amount of uncertainty in any measurement. For example, you will be saying kind of a percentage like, okay, 99% accurate, 98% of the time it is accurate, something like that. Precision is the reproducibility of the measurements. So when you measure the same value number of times, it will give you very, very similar or the same number. Resolution is the smallest change that can be measured by the sensor. It could be like 0.1 or 0.01 or whatever the resolution or the smallest change. Sensitivity is how strong is output signal relative to the input. Or in other words, minimum input of physical parameter that will create a detectable output change. So how much is the physical parameter need to be changed in order to create a detectable output in the sensor. Hysteresis is a measure of the property that the sensor output changes is independent of the direction of the changes of the input parameter. What does this mean is that in simple terms that the history of the sensor measurement should not impact the current measurement. The best way to explain is that assume you have 3 rooms, normal room temperature, freezer room, and then the steaming room, which is high temperature. And then assume that you are doing an experiment that you measure all 3 rooms in different orders. First, you measure the normal room, then you measure the freezer room, then you measure the steam room. And the next experiment, you first measure the freezer room, then measure the steaming room, and then you measure the normal room temperature at the end. So what hysteresis means is that despite what is the order, the values should be the same in each room. The next characteristic is the linearity, which means the output is directly proportionate to the input. Not all the sensors actually follow the linearity, but if it is following, that is really good. And then the response time. So the time for the sensors to change to the new output state. So how long it come to the measure the temperature or humidity or pressure or whatever the parameter you're measuring. There are a few different concepts we need to learn when we are studying the behavior of sensors and actuators. So the first one we are going to talk about is the sensorial deviation. So how the values sometimes change or deviate from the correct value. As we discussed before, every sensor has a range which has the maximum value and a minimum value. So within this maximum and minimum value, you usually find a linear relationship between what you're going to measure and then the electricity they produce. So you can have like a one-to-one mapping using an equation roughly that if the temperature is increased by 1 Celsius, this much of electricity will be generated, something like that, or whatever the output is proportionate. But outside of this range, it may be not linear. So that is why there's always a range, because it becomes quite challenging. It is possible to have multiple equations in order to set for a curve in a particular graph. We will be looking at one of those later on, but it's going to be challenging. So usually you try to find a linear relationship between the phenomena and the output. For example, if you look at the typical blood pressure transducer, may have the sensitivity rating of 10 millimeter of mercury. So that is, it will generate 10 millivolts output for every unit of volt of excitation potential and each millimeter of mercury of applied pressure. So that is how you measure the blood pressure. The sensitivity of a sensor under real conditions may differ from this particular value specified. So we say that it is 10 millivolt is the amount of the sensitivity. But if it is difference, that is what we call sensitivity error. So let's say you have the pressure transducer discussed above, will actually have a sensitivity of 7.8 instead of 10. So if the output signal differs from the correct value by a constant, so always it is a constant, then it is a offset error or a bias. We call it offset because it is always a particular constant. So you can probably either replace the sensor or you can use a software layer to add some the offset and make it work. But if this offset value is changing over time, which is part of the calibration, then it becomes troubling to recalibrate and perhaps add this particular gap between 7.8 to 10. And these do some manual calculations you can do, but then again you need to think about how critical these measurements are when you are correcting these issues such as offset errors and bias. Non-linearity is the deviation of a sensor's transfer function from a straight line transfer function. In this figure or the graph, you can see different transfer functions. Basically, there are straight lines which can be used to measure the changes of the voltage and the phenomena that you are going to measure. As we discussed earlier, sometimes the the graph doesn't seem exact linear. So what you are doing is you try to create approximate and then try to measure the difference. So that is the difference between the ideal transfer function, and then you have to create different functions to handle or track different slopes, and then try to match in an approximate way. So most of the sensors have a linear behavior, but if they don't have, then you will end up creating a non-linearity function approximation to the real world. There are two ways to do that. So you can either approximate and have some kind of a small error, accept it, or you can have mathematical functions that will trigger different part of the measurement. So if you know at what point it becomes the slope differs, then you can divide this graph into multiple areas, and then if you look at the voltages, and if the voltages pass by a certain number, then you change the equation. So rather than using one ideal function, transfer function, you have multiple transfer functions with dynamically change based on the change of the physical phenomena. So if you're measuring temperature or pressure, you say that, okay, from this point to this value, this is the transfer function, and after that you use the transfer function to a different one. Another reason to deviate is something called drift. So if the output signal slowly changes independent of the measured property, we call this a drift. So long-term drift over months and years could be due to physical change of the sensor. Those kind of drifts could be addressed in the software layer by looking at the other sensors and doing some kind of software layer calibration, so adjusting the values, incoming values. But again, it's a trade-off between when you want to change it, hardware, or physically deploy or replace the sensors, versus changing the values and adjusting to the drift. On the other hand, the noise is again a random deviation of a signal that varies in time. It is very difficult to handle noise. If the sensor started giving noise which is random deviation, pretty much you can't do anything other than try to replace it. But if it's a drift, then you can actually up to certain level you can correct it. In order to correct noise, you probably need multiple sensors around it. So look at the nearby sensor, then try to get approximate or something like that. So other than that, there's nothing much you can do because of the randomness. Another way of deviating sensor values from the actual value is hysteresis error. So this type of error causes the sensor's output value to vary depending on the sensor's previous input values. So I gave you a previous example. If you have hot room, cold room, and a normal room, ideally if you measure the temperature of the 3 rooms in 3 different orders, hot, cold, normal, or normal, cold, hot, or whatever the order, they should produce the same results ideally. But as you can see on the figure, sometimes temperature going up and down is not necessarily the exact linear function. So if that is the case, it will create an error. So this error, in simple terms, occurs when the previous input values started to impact the current measurement. Typically, these kind of errors could happen in analog sensors such as a magnetic sensor. So if you are heating leads to bend a metal stripe, then it will take some time to come back to normal. So until it comes back to normal, the output values could have some hysteresis error. There could be another type of deviation or error that could happen in sensor measurement. If the sensor has a digital output and the output is essentially an approximation of the measured property, then there is a difference between the actual value and the measured value or the quantified value because of the digital output. So that small value is something called quantization error. Another type of error or a deviation is a dynamic error. If the signals are monitored digitally and then the sampling frequency could cause an error. What does this mean is that when you're sampling frequency, the actual measurement could be fluctuating. And then because of this fluctuating, for example, if it is a temperature, it may be going up and down. For example, if it is measuring a ball bearing or a motor, the temperature could go up and down. So based on the sampling, you might not capturing the exact temperature because it is measuring in a single point of time, and then it also changing. So that kind of errors we consider as dynamic errors. Aliasing errors is another type of error that may occur if the input variable or the added noise changes periodically at a frequency proportional to the multiple of the sampling rate. Aliasing errors are hard to detect and almost impossible to remove using software. The solution is to use a high enough sampling rate, or if this is not possible, to use an anti-aliasing filter in front of the analog to digital converter to eliminate the high frequency components before they get into the data acquisition system. In more simple terms, if the outside world is changing at a faster frequency than the frequency of the sensor, which actually samples the phenomena, then of course it could end up with an error because the outside world is changing fast, and then the sensor cannot don't do sampling enough to capture the changes of the real world. Finally, it is worth noting that the sensors may up to some extent be sensitive to properties other than the property it is measuring. For example, some of the sensors may influence by the temperature or the humidity, even though they are not temperature or humidity sensors, they are supposed to measure something else. But the environmental factors may be affecting that. So those kind of errors could also could be reasons for deviating from the actual values.